Welcome back. This is our fourth tutorial. Today's example covers Thevenin equivalent circuit. Given the following circuit, we would like to find Thevenin and Thevenin. Let's first find Thevenin. By definition, Thevenin is the open circuit voltage. From the figure, we notice that the output terminals AB are already open. There is no node connected to them. Therefore, Thevenin is equal to VOC, and this equals to VAB. Now let's use nodal technique to find Thevenin. I'm going to choose these nodes for the node voltages and the bottom node for the ground. And here's the first equation for node 1. I'm not going to discuss the details of the terms since I've already done this in an earlier tutorial. However, it's always a good practice to count the number of branches connected to the node so you don't miss a term in the nodal equation. And now for node 2, we have the following simple equation. Okay, we have two equations but three unknowns. We therefore need a third equation that involves the voltage V0. From the figure, V0 is the voltage across the 3 ohm resistor, which is the voltage from node 1 to ground. This voltage is the same as node voltage V1, which means that V0 is equal basically to V1. And this will be our extra equation. So we have V0 is equal to V1, and then we can substitute now for V0 into equations 1 and 2, and this gives the following two nodal equations. This is the equation for nodal 1, and this is the equation for the second node. Now, solving these two equations gives V1 equals 6 volts and V2 equals 3 volts. Now, since Thevenin by definition is the open circuit voltage, which in this case is the voltage from A to B, then recognizing that terminal A is connected to node 2 and terminal B is connected to ground, then VAB is basically V2. Okay, and therefore Thevenin is equal to node voltage 2, which is 3 volts. Now let's try to find Thevenin. We know there are several ways to find Thevenin. The simplest method is to find the equivalence resistance. However, since there's a dependent source, we cannot use this technique. Instead, we will find Thevenin using two other techniques. The first one is by finding the short circuit current, and in this case Thevenin is given by Thevenin divided by I short circuit. And the second method is to use the V-test method, and in that case Thevenin is given by the ratio of V-test over I-test. So let's first try the I short circuit method by adding a short circuit at the output terminals, where ISC stands for I short circuit. Since we've already demonstrated nodal and mesh techniques before, let's find I short circuit by using source transformation. From the figure, it appears that there are two places where we can use source transformation. The voltage source in series with the 6 ohm resistor and the current source parallel to the 2 ohm resistor. If we do source transformation for the voltage source, we will end up with 4 loops. So this complicates things for us. However, if we do source transformation for the current source, then we end up with only two loops. So let's do that. Notice that source transformation can also be used for dependent sources. Now, to find the value of the voltage source, we use Ohm's law. So multiplying the current source 0.25 times V naught by the value of the resistor 2 gives the value of the voltage source 0.5 V naught. And here is our transformed circuit. Notice that the resistor value does not change. Okay, now let's add currents I and I1 to these branches. Of course, the current in this branch is I short circuit. Our objective is to find I short circuit. So let's write a KVL equation for the left loop. And this is what we have. Minus 18 plus 6I plus V naught is equal to 0. Now let's write another KVL equation for the right loop. And we have minus V naught plus 0.25 V naught plus 2I short circuit equals to 0. So far we have two equations but three unknowns. We have I, V naught and I short circuit. Therefore we need an extra equation. Let's try to replace the current I. We can do this by writing a KCL equation at this node. This gives the following. I is equal to I1 plus I short circuit. Now these are three equations, but we have now a fourth unknown, which is I1. However, I1 can be expressed in terms of the voltage V naught through Ohm's law. So we have I1 is equal to V naught divided by 3. Now we can substitute equation 4 into equation 3 to get rid of the current I1, and then we can substitute the resultant equation into equation 1 to get rid of the current I. By doing so, we get the following two simple equations. So these are two equations with two unknowns. We can solve these two equations to get V naught is equal to 4 volts and I short circuit equals to 1 amps. And finally, R Thevenin is given by V Thevenin over I short circuit, or 3 ohms. Now let's try to find R Thevenin using the V-test method. To use the V-test method, we need first to deactivate all independent sources. In our case, since we have only one independent voltage source, we deactivate it by replacing it with a short circuit. We will then need to add a voltage source at the output terminal as follows. This is how the circuit looks like. Notice that the 18-volt source is shorted out, and this is the voltage source that we added, VT, and we have a current coming out from VT, which is IT. And in this case, R Thevenin is equal to the ratio of V-test over I-test. Again, to find this ratio, we will use source transformation to simplify the circuit. And since we've already done this, this is how the circuit looks like. I've added two currents, I1 and I2, to help in writing the equations. Where do we start now? Since we need v-test and i-test in our equation, we can start by writing a KVL equation for the right loop. So let's do this. We have minus v0 plus 0.5 v0 minus 2 it plus vt equals 0. The terms in the equation look fine, but maybe some of you are questioning the third term. Why is it negative 2it? The reason for the negative sign is that we are writing a KVL equation in the clockwise direction, assuming a voltage drop. And since it is in the opposite direction, then according to the passive sign convention, we need to add a negative sign. Now this equation has Vt and It, but to find the ratio we need to express V0 in terms of either Vt or It. From the figure we notice that V0 is related to the current I2 by Ohm's law. So let's write the equation. V0 is equal to 3 times I2. Now we need to replace the current I2. One might think, okay, let's write a KCL equation at this node. Well, if you do that, then you will introduce the current I1 into the equation. So this may be not a good idea. However, if we look closely to the circuit, we can find an easy and better way. Notice that the current IT goes into two parallel branches. Therefore, we can express I2 in terms of IT using the current divider technique. And by doing so, we get the following equation. I2 is equal to IT times 6 divided by 6 plus 3, or I2 equals to 2 over 3 times IT. Now substituting equation 3 into equation 2, we have V0 is equal to 2 times IT. Also, we can substitute V0 back into equation 1, and this gives the following equation, which only has IT and Vt. And from this equation, we can find the ratio of Vt over It, and this gives us 3 ohms. And this is our Thevenin. And this is the same result we've obtained in the previous technique. And that's the end of this tutorial session. Get ready for the next and last tutorial.